Okay, hope everybody got a chance to stretch your legs a little bit. We're gonna get started with our next one. Harley Schreiber graduated from the University of Alberta in 1986 with a Bachelor of Science degree in Chemical Engineering. He is currently a senior process engineer with Westech Engineering and has focused on process design of solids liquid separation equipment for most of his career. Welcome.
Okay, thank you. So today I'm going to talk about mine water treatment system, active treatments, PhysChem systems, but I want to focus on the clarifier part of it. There's a lot of decisions that need to be made in the design of that. So we'll focus on looking at some of those designs and what criteria you would use to select different types. So if there was a typical system, which there isn't, there's a lot of options in an active treatment system. We might start with something like this. So the mine water is going to enter what we need to treat. It could be low pH, acidic, but it could also be near neutral pH or even alkaline. But it's going to contain these, contaminants that we need to get rid of as well as neutralizing it. Iron, aluminum are two key ones that we often see that we need to get rid of: arsenic, manganese, sulfate, and there's other metals, heavy metals, lead, zinc, copper. And so the way the treatment in simple terms is we're going to raise the pH, precipitate out these dissolved metals, turn them into a suspended solids, and then remove them with our clarifier. So the first step often in this is the CO2 removal. So that's the first step in raising the pH. You can remove that CO2 in two different ways. One, lime can be used to basically turn it into bicarbonate. But to conserve on lime, you can strip it off with aeration. So often there's a decarbonation step, and it's an economic trade-off between more lime consumption or using energy for the air. Okay, so the heart of the system then is this reaction part where this is where we're raising the pH, and also often aeration is used. Iron particularly is going to precipitate out in the oxidized form. Arsenic, there's benefits in its removal by oxidizing the arsenic as well. There could be other oxidants used, chemical oxidants. Peroxide is commonly used. And also, I guess I forgot to mention the most important thing, the lime addition. It could be other forms of alkaline addition, limestone, caustic. So as we, like I said, raise the pH, the dissolved metals are turned into a particulate, and that's where the clarifier comes in. We need to remove those solids. They settle by gravity to the bottom of the unit where they're removed. The clear water now, which is containing very low levels of metals, is removed out the top as a treated water. So a modification to this process is sludge recirculation. So we can take a portion of this consolidated slurry from the bottom of the clarifier, pump it back into the reaction tank, and now you have these particles which are nucleation sites or seed particles for the precipitation. So this helps to build up larger particles that are going to settle faster. It helps with the reaction times for the precipitation. And in the last presentation, it was mentioned the HDS process. So that's a further modification or an improvement to this process, where instead of mixing the lime directly with the mine water, we mix that lime with recirculated slurry. So now the lime is coating those particles, creating a very high pH zones around the particles, so the precipitation can occur right on the particles. And as you're recirculating, you're building up larger and larger particles, settle and compact better. In fact, underflow concentrations with this HDS process can be maybe up to 10 times or more higher concentration than just a once-through process without that recirculation. So as I mentioned, this is the part we're going to focus on from here on. There's a lot of choices in clarifier. Westech started supplying clarifiers in acid mine drainage in the early 90s, well over 50 installations. And from that, we and other manufacturers have developed different components internal to improve the performance. And there's no one solution to get the optimum, but there's a lot of choices, and we'll talk about some of those as we go forward. So I'm going to describe 3 different types of clarifier thickeners in the next slides, and what their features are and how they're different from one another. But before I do that, most people use the word clarifier and thickener kind of interchangeably. They're fundamentally, it's the same machine, but it's how you focus on the design. A clarifier, you're focusing on producing a clear effluent. So you're going to do things in that unit to make clarification happen. Make sure you have enough clarification detention time. Make sure you have good flocculating conditions in the feed well. A thickener is focusing on producing a concentrated waste stream or underflow. So you need to make sure you have enough raking torque, rake capacity, enough time for those solids to compact and consolidate. So you're focusing on that. But there's no reason you can't do both of these functions in one unit, and that's often the case. And so it's really not a clarifier or a thickener, it's kind of both. So this is a standard unit. Just in quick terms, the feed, again, it contains those particles, the solids that we've removed, metals. It goes into the feed well where the energy is dissipated, and this is also the point where flocculant can be added. Could be added a little bit upstream, but flocculant's often added here. And flocculant it's a long chain polymer that attaches or grabs onto these fine, small particles, and then with the mixing in there, more particles get grabbed on and they agglomerate, making larger particles that settle faster. The slow turning rake mechanism with blades moves the consolidated slurry to the center where it's discharged in this cone, and an underflow pump is used to remove that waste sludge. The clear water rises to typically a peripheral launder where the treated water is removed. So that's a standard unit, no special features other than there's a lot of details in making sure you get the design right, of course. Okay, this next unit is truly a clarifier. It's a solids contact clarifier. It also has a rake mechanism that's just not shown here. But the way this unit works, its fundamental principle is this high flow impeller. So it's an impeller that's pumping. It's a low head, high volume pump that creates a circulation of consolidated solids or slurry down on the bottom. So now it pumps it up into this contact or reaction zone. So now, just like the previous, in an external reaction tank, you have all of these solids moving around, mixing with the incoming feed. And then when we add the lime, in this case, we have that exact reaction that we had before in the external reaction tank. So you get the precipitation onto these particles. You have a high, it's really the same, but we actually are recirculating way more solids than you can with an external recirculation. So again, you're building these particles. We can add flocculant in this location. So growing particles, flocculating and producing a slurry that settles very quickly and produces a clear overflow. Okay, so that's a solids contact clarifier. And then the final one is called a flocculating clarifier. And has the same principles as a standard clarifier, but we modified this feed well. So the feed well is a little bit larger, provides a little more retention time for flocculation, and also has this impeller or mixer with the right energy to promote flocculation. So it's like a standard unit, but with enhanced flocculation. So if we'll try and quickly look at where we might use one versus the other, if we look at a solids contact clarifier, if you have a once-through system where you're not recirculating solids externally, this is going to work very well because sometimes there may not be a lot of metals precipitating, and if you don't have a lot of solids in the feed, it's not going to flocculate well on its own. The particles just don't have a chance to grab onto that flocculant. So by recirculating those solids continuously, building up the concentration, you create better and better flocculation with this. You can't aerate in this unit for oxidation, so you probably, if aeration or oxidation is needed, you'll need a chemical oxidation. But as I mentioned, the unit does produce very high clarity and improved settling rates, so you can actually reduce the footprint of the unit. Now, the downside to this design, like I said, it's a clarifier. You can't really produce a really thick underflow. That draft tube is right near the bottom where the consolidation happens. So you do have a more dilute waste stream that with a little higher volume of sludge you have to waste. Okay, if we look at the flocculating clarifier, this unit is used a lot of places where the standard unit is used, but you do need a bit of external recycle often because you want to build up the solids concentration so it flocculates, but now you have that enhanced mixing in there for flocculation. With an HDS process where you get a very high concentration going to the unit, it's probably not that much of an advantage. It still would be helpful, but it's an added cost that probably isn't needed, and flocculation without the mixer is probably just fine. Again, it's with the extra flocculation, you're producing a clear overflow, but unlike the solids contact clarifier, you can actually produce a thick underflow as well, so there's a benefit. And then finally, the standard unit, very well suited to the HDS process because flocculation with that concentrated slurry is going to be done very well just in a standard feed well. And of course, you're producing a concentrated underflow. So those are some of the first considerations you need to make in choosing what type of unit to use for your treatment system. Okay, just quickly on tank selection. Obviously, the tank is a very expensive part of the clarifier. On the left is a concrete tank. It's more expensive upfront cost, but maintenance-wise, it's going to last a lot longer. Steel tanks are very common too, but they're less expensive to build, but you need upkeep because corrosion in these systems is prevalent, so you need to periodically paint and touch up paint and repaint. So long-term, a lot more maintenance. So that, if we look at steel tanks, they're still commonly used, a lot of concrete, but steel tanks are used. There's a couple of basic types. The first is an elevated design. So this is a steel shell, tank shell, steel bottom, and it's supported on often, usually, steel support structure. It's a very good design for smaller diameters. You can put the discharge pump right next to the underflow, so there's no problem with moving thick underflow slurries with this. But like I said, as you go bigger in diameter, it becomes cost prohibitive. They get very expensive. So in that case, when you go to larger diameters, like 130 foot or higher, you can do an anchor channel tank. And in this case, it's just a steel shell, and it's on a concrete foundation or a ring wall, and embedded in the concrete is a steel angle. So that's where you can weld the side shell onto that angle. Very inexpensive, just rolled plate welded together. The disadvantage with this design is it's difficult to put the underflow pump directly next to the discharge. So it needs to, because you have to excavate a tunnel, so that means confined space issues and say other safety issues. So you usually need to put the pump outside the perimeter, and now you have a longer suction pipe line. It's still okay, it's used effectively often, but you may need consideration like flushing the line or an alternate, a duplicate suction line in case there's problems. So that unit is very inexpensive, commonly used on large diameters. Okay, so the internals, like I said, we've developed different methodology designs to help with the performance. The first thing we look at in our design is putting the rake blades. We mount these on posts, and this lifts this rake truss structure up. The common problem in operating a thickener is buildup of mud, consolidated heavy masses in front of the rake arm. By lifting these up with these posts, often called fixo posts, the thick mud has a place to pass over the blades and not accumulate on the rake arms. We can further enhance that using a low profile rake arm. So now you've removed that truss and the buildup potential of solids on that. Other things we look at, rake lift mechanism. If you do get a high torque condition, you're building up solids, the rake will lift up a couple of feet. It gives the operators time to correct situation. Maybe reduce the solids inventory, maybe they're adding too much flocculant. So it buys time for them to correct the process and get things under control. We look at floor slope. We need to make sure the floor slope is steep enough to assist the rakes with gravity to move the sludge to the center. And there's enhanced feed wells. There's a number of different ones out there. This is our even flow feed well. It's a two-stage unit, so the feed comes in. The first stage dissipates that energy and distributes the feed evenly all the way around 360 degrees. So when it comes out into the bottom section, there's good mixing for flocculation, and again, the feed is distributed evenly. You're using the entire area of the thickener. Okay, so this, just to pull it all together, all of those things are important, but if you don't size the clarifier or thickener correctly, or if you don't get the process right, it's really bad. So recommend lab testing. On the left here, we have a jar testing apparatus. And here we can simulate the process, simulate the chemical precipitation. But at the same time, you know, as equipment manufacturer, we have our design sizing methods. So we can do settling tests with the solids that we're precipitating. So, let me back up. So with this, one of the key components in sizing is looking at the mass of solids per time per area that you need for that unit, okay? So we call that the unit area, the area per mass per time of solids needed. So with these jar tests, we're gonna determine things like reagent dosages, the lime usage, how much reaction times are needed, what the sludge production rate is. We need to know how much sludge we're gonna produce, as well as can we get the metals down to the residual levels we're looking for. Excuse me. Okay, and then finally, when we're simulating the HDS process, we learn that the underflow concentration is going to increase as the amount of recycling increases. But increasing this recycle puts more tons of solids to the unit. So the thickener actually could get bigger, but also at that same time with the HDS process, we're settling solids faster. They're more compactable, they settle faster. So there's two opposite forces. More solids means possibly a bigger unit, but faster settling means it could be smaller. So of course we need to do an iterative calculation. So we need to, what happens when we increase the recycle ratio and change our sizing criteria on the thickener? It's an iterative process. We can optimize the diameter of the clarifier and also make sure that we have our sizing of our reaction tanks all done correctly. So in conclusion, clarifier, you know, it's a critical part of that process of the mine treatment, water treatment. Many decisions need to be made on the design of it, and we need to get it right through our laboratory testing. Typically, we'd like to do those tests on site, so we have the fresh source water that hasn't had time to degrade. That's all I have.